Is my screen visible? Can you see my screen?
Yeah, it is visible.
Okay. Okay. Hello everyone. Welcome to week 3 of problem solving session for NPTEL course Introduction to Operating Systems. And this week is about processes. So we will be solving questions, quiz type questions, similar to your quiz assignments. And so we will look at first the question and then I'll give you time to answer it. And after that we will discuss the solutions. So here our first question is, you're given us program C, like it has C syntax, and um, the program has a for loop here, which is the iterator is from 1 to n. So I is equal to 1 to I is less than n, and it is incremented on every iteration. Then inside you have a fork call, and then you have a print statement os and print statement printing nptel. So you are asked the number of times os and nptel will be printed, and these are your options. So you can try the question and you can try to answer it while I'll try to set up the whiteboard. Is the question clear? Do you have any doubts? Did anyone try? What does system, what does a fork call would do? What is fork? Anyone? What is fork? So let's look at fork. I am not sure if you've, I think, let's just look at fork. Okay, so fork is a system call and it is used to create a new process in Linux and Unix systems. So when you write fork in your program like this, as you're given in the question, and that time this will create a new process, which we will call the child process. And you also have, and the original process which has this fork system call, that is called the parent process. So after fork there will be two processes, one is the child process, one is the parent process, and then the both the processes will run concurrently. Okay, if there are two processes and these are the only two processes, they can run concurrently, based on the resources and scheduler algorithms, etc. So after this new child process is created, the both processes will execute the next instruction following the fork system call. Okay, so whatever is the next instruction, that will be executed in both of the processes. The child process uses the same program counter, the same CPU registers, same open files which used in the parent process. So it's actually a copy of the parent process. All of the data and code etc. is also copied, and all of the process state is also copied. So it has the same program counter, registers, CPU, open files, etc. Now when this fork is called, okay, this is the function call, right? It's a system call, it's a function call, it will return some value. So it can return three types of values. A negative value like -1 indicates that the creation of the child process was unsuccessful. Now why can it be unsuccessful? Because it is possible that there are not enough resources in your system like memory, and so the process cannot be created, or any other error could have happened in the code, kernel code. Or it may return 0. So when does it return 0? So it returns 0 to the newly created child process, and it returns a positive value which is actually the process identifier, PID, to the parent process. So the value contains the value is actually the process ID of the newly child process. So in your code here, when you have this fork system call here, this will return some value. It will return 0 in the child process, and it will return a positive value. If the fork is successful, then it will return 0 in the child process, and it will return positive value in the parent process. Okay, now that positive value is actually the PID, process ID, of the child process. Every process in your system has a unique identifier. Usually it is it's an integer, it's a value, not an integer, it's a positive integer, and that value is the process identifier, which is used to uniquely identify every process in your system. Okay, now here we do not have one single fork, we have multiple forks being invoked again and again, because this code is part of the for loop. So since for loop is executing here n-1 times, so fork system call also will be executed multiple times. And the question is asking you to, like, basically it is something related to how many processes will be created, and what code will execute in those processes, which depends on whether the process is child or it's a parent process. Now just let's look at maybe an example for this, and then I'll ask you to again try that question. Okay, but we can look for a simple example. Yeah, so let's look at here. Okay, we have here 3 fork system calls. So first one, like if, so this is if condition is there, okay, and then inside we have fork. So first fork will be executed. So what will happen? If it is successful, then it will return 0 in the child and non-zero value in the parent. But so initially you have only one process, and let's call it P. The process, we are calling it P because it's a parent process. So this is your process. The circle here, this is signifying a one process. So initially you will have only one process P. Now when you execute the first fork, this first fork system call is executed, that time one child process is created. Parent will stay, the parent will be there still, a new process is created. Let's call it C1. Okay, C like child 1. So now you have two processes at this level. These are the two processes, P and C1. After that After that, both of the processes will start executing from the next instruction. Okay, the next instruction will means your code will come here. That is, again there is one more fork. So now when there is one more fork here, now the parent will execute this fork. So when the parent execute this fork, it will create one more child process. That is this part of the tree. The parent will stay there, parent is still executing, and but it would have created one more child, and let's name it C2. Okay, at the same time, C1, that is your previous child, also executes this fork, and it will create one more process. So C1 is there and it has created one more process, C3. Okay, now it depends on okay, if you understood this much, I think that's enough, because the next is like conditional. Okay, next is conditional. So this will be, it depends on whether it's true or false, which will depend on the value which fork is returning. So that I'm just skipping for now, but this is how the fork system call will work. Okay, and now given, if you have any question, then you can ask me about the fork system call. Otherwise, you can try the question again. This is it's a bit, it can be a bit complicated, but just look at the question once more, try it again, and then we will discuss it. Any question about fork? If you don't understand, then I can explain fork again. Okay, fork is a system call. So fork is a system call, and as I was, so I'll just use this again, or I can, okay, fork is the system call. Okay, what is a system call? System call is actually an interface which the operating system provides to the application, user applications, so so that it can, like, to, it's an interface which is provided by the operating system to the applications to use some services of the operating system. Now here the service which operating system is providing to the user application is to create a new process. So you have a process and that is running currently. Okay, you have a process and it's running, and let's say you want to create one more process. Now you can invoke the fork system call, and then it will create one more child process for you. I'll just use the whiteboard maybe. So it is a system call. Okay, system calls are function calls which when they are, when it is executed, then the control goes to the operating system. Now the fork system call, it provides the service of creating a new process. So it's a system call to create a new process. Okay, so you have a process already running, like this program. Okay, when you run this program, when you compile it and then you run the binary, what happens? You create a process. Now when this process is running, now if we have a fork call in this, the fork is actually a request to the operating system to create a new process, and that new process is called the child process. It's just the this process, the original process will be called then the parent, and because this is creating a new process, that new process will be called the child of this process. So that's it about, like, that's what just fork does. It just creates a new process for you, and that new process will, and the parent process will have the same code, and everything else will be also copied from the parent process to the child process. And uh, and both of the processes will be in they can execute simultaneously, they can execute concurrently, and both of them will start executing from the next instruction after fork instruction. Okay, let's now look at the question. So you just look at the question once more while I'll copy the source code. Okay, so this is your code here. So the first, you have integer variables, okay, then there is a for loop, and inside this loop you have I is iterated, the iterator is from 1 to less than n. It's incremented by 1 on every iteration. That means your for loop will run n minus 1 times here. Okay, and now when you run this program, the first time this program is run, that time the first iteration of the for loop will execute. In that iteration you have this if fork equal 0. So what will happen, this fork here will be called, this fork function call will happen, and when this fork function call will happen here, this is the system call, and at that time a new process will be created. Now you have here P, which is your original program. Let's call this your original program P. This main function which is executing inside this P. Now when P call has this fork system call, what happens is that a new child process is created. Let's call it C1. Okay, and your parent is still there. So this was like all processes in your system earlier, and now your system have these processes. Earlier your system had process P. After fork is executed, now your system have two processes, C1 and P. Now you have two processes. Now both of these processes will start executing simultaneously from the next instruction after fork. Okay, so what is the next instruction after fork? It is a compare. So when we say instructions, now in the C code you have only one statement, if fork equal to 0, but when you have compiled it and in a binary, this if statement will be a bunch of instructions, and in that bunch of instructions, the first is the function call to the fork, that is the fork call. After that you will have some instruction to compare the output, the return value of the fork. Okay, so now we are going to compare the return value of fork. And now as I said earlier, fork returns 0. Okay, here I'll write fork returns 0 in child process and returns the positive value, or which is the PID, in the parent process. Okay, so now this is your child process, right? So in the child process it will return 0. That means this if condition will be true. Okay, so in this the if condition will be true, and therefore it will print here OS. OS will be printed here. But in your parent process P, fork will return some positive value, not non-zero value. So this if condition will be false and the print will not be executed. Now what happens? Now in both of these processes, the for loop will continue, right? Because both of the processes will execute. Now what happens? I was 1, it was incremented, it will be incremented to 2, and the for loop will execute again. So in both C1 and P, they will start executing from the next iteration of the for loop. So in the next iteration of the for loop, there is again a fork. So when C1 executes this fork, it will create one more it will create a child process. Now this child is child of C1. Okay, it will create a child process, let's call it C2, and C1 is still there, so it will be there. Similarly P will execute, it will create a child, we call it C3, and P is still there. So now in your system, these are all the processes. Now you have 4 processes, P, C1, C2, C3. Okay, now in each of these, which code will execute? Now when you will come to C2 is the child, that means fork returned 0, so here OS will be printed. But C1 in this case is the parent now. Okay, so it will be it will get a return value which is positive, non-zero, so that's why here OS will not be printed. C3 here is the child, and here OS will be printed, and P is actually here still a parent, and therefore OS will not be printed. I mean, this if condition will be false here, and it will be true only for C2 and C3. Now you have 4 processes. Now all of these 4 processes will start executing from the next instruction, that is from the next iteration of the for loop, which is I is equal to 3, and the process, this will keep happening until the all of them finishes. All the processes, new processes will create in the next iteration, then new more in the next iteration, and so on until all of them terminate. I mean, all of the processes, the for loop will finish. At that time, no more new processes will be created, and your program, all the different processes will start terminating.
Excuse me, ma'am.
Yeah.
So basically, this C1 and P, they are the parents, right?
Yeah, here they are. Yeah.
So they will the downward.
Yeah.
So it can create more child, right?
Yeah.
Okay, then
C2
then
can
why,
also create.
So why did you stop here till like
No.
C2, C1 and
I can write the other levels also, but I just stopped here I just stopped here because I can go on till n, but here we can, this I just draw to explain how it is working, and now we can imagine or how it will continue to work. Now I'll go over the next iteration also, but then we can imagine like how it is going to work.
Thank you.
Yeah. For this, for the tree that I have created here, you can assume that this is the tree when n is equal to 3, right? If n is equal to 3, then this tree would have been created. You would have 4 processes by the end.
I didn't get this point. Can you tell me again?
Yeah, I'm saying that if instead of n, if your program had here I is equal to 3, then at I is equal to 1, the first iteration, this would have happened. One child process would have been created and you had parent. Then I is equal to 2. In the second iteration of the for loop, you would have created 2 more child processes, C2 and C3. After that, in the third iteration, then I would become 3 and the for loop would break here at this condition check. So if if n were 3 in your, I mean this for loop were the for loop, here n was 3, the condition was I is less than 3, then this would have been your process tree. I mean by the end you would have only these 4 processes in your system: P, C1, C2, C3. Is that clear?
Okay.
Is it not clear? I'm only saying that I'm just putting a numeric value in place of n, and I'm saying if n were 3 in your code, then if you would run it, when n is some value that you don't know, it's a variable, right? I'm saying that if this variable value is 3, then at that time this is the process tree which would be created. These are the processes that would be created in this order.
Okay, ma'am.
Okay, so by the end of the for loop you would have 4 processes running in your system, and these will, and like this is the way they would have been created. First P was there, P created one child process, C1, then C1 created one more child process, and similarly P also created one more child process. In total you would have 4 processes. Does anyone have any questions so far? No questions? Okay, if there is no question, then let us look at the, I mean what is your, oh my God. I'm sorry, there is some noise. I'll just check. Hi everyone. I'm really sorry. There is some construction work going on. So I'll just uh, you can read the next question that I'm pointing to, and you can write your answers or questions in the chat box. I think it will take only 5-10 minutes. Any doubts? Any answers to the question number 2? I'll come back to 1 in a while once there is not noise. The question is saying that the program to compute the sum of first 5000 numbers can be divided into 4 subparts and executed on 4 CPUs using either fork or threads. The reason why we prefer fork is because large portions of data code between the 4 subparts are very similar and need not be duplicated. Is it true or false? So in the first question we saw that we use a fork system call to create a new process, and when we create a new process, that process and the previous process, they share the code, right? They share the code and the data, and not share, I mean there are two different processes, so the data and code is actually copied. It's it's same, like the code is same and it is copied to the other process, and then they can, and the physical memory can be shared also, I mean the code pages can be shared, and in that manner we can execute like the same code is there which can be executed by multiple processes. So I think there is no noise now. Do you have any thoughts about this problem? I mean, do you think that so threads is also one of the mechanisms by which we can divide a program into multiple executions, into uh, multiple executions, like it can execute parallelly, okay? So that is there, and fork is also one of the ways by which we can execute, we can divide the program into different subparts, and then these subparts can execute on different CPUs. Any, I mean, what do you think? Is it true, false? Why is it true or why is it false? Any answers? Okay. So do we usually, would you prefer fork over threads to do this? Okay, that's all right. But would you prefer fork or over threads? So, yeah. So since both of them are possible, possibilities. You can either create 4 different processes and then they will divide the work, that is adding these 5000 numbers, and can be divided between them, or you can create threads. Now thread is actually a lightweight process. It's called a lightweight process because your process itself, so yeah, there are not different processes inside your process, one process only. When you create a thread, that means those threads, uh, they will share they will the threads, they have they are part of the same process. They are not different processes, but they can run on multiple processors. So that's why it is lightweight, in the sense that you're not creating different processes. There is only one process. Each thread has its like its own registers and its own stack, but they share the heap. So they will have different registers and stacks because each thread will be executing some different part of the code or doing something else. So that is why, but it is a lighter mechanism. It's a lightweight mechanism because you have only one process in your system, while with fork you will have 4 processes in your system, which is actually, so when if you have, here we have 4 CPUs, so that's not a problem. The four processes will be running on 4 CPUs, but the 4 threads can also be run on 4 CPUs. So the answer to this, I mean, the reason that they have given is a valid reason, that if you use fork, then large portions of the data or code between the 4 subparts, they are actually quite similar, because the data, which is the 5000 numbers, that is common to all the code. The code is also, you are just adding the numbers, is also similar. Same code probably is being can be used, and the code and the data will not need to be duplicated, in the sense that it can have only one physical copy and all of the processes can map to that, can have a mapping to that physical pages. But it is not preferred way. So the answer would be false, and not because the reason for using fork is not correct. It is not a preferred way to would not be a preferred way to do this, because using threads you will have much lighter lightweight execution. Okay, you will not have multiple processes in your system. You will have only one process. That is, the resources, less resources will be used. The data will not have to be copied or anything, and but you can still have parallel execution. The task can still be parallelized. So the answer to this will be false, because threads would be a better fit here. Does that make sense? Any question? Okay, if not, I'll just return back to this question number 1 on the whiteboard. So the question is actually asking how many times NPTEL and OS are printed. So now let us look at this. We have this example, and here okay, so in this example here, if n is equal to 3 only, let us assume that your question was such that n were 3. Okay, then try to answer the number of times OS is printed and number of times NPTEL is printed. So this is the tree that would, this is the process tree. Okay, this is the way processes would be created in your system. At the end you will have these 4 processes, and as we discussed here, in C1 the child process 1, OS will be printed 1, then C2 will be printed here, then C3 will also print OS. Okay, just look at the, yeah, so here as you can see, in each of your child processes, so in each of your child processes, because for every child process this will be true, right? In the child process, every time you will return 1, in a child process, what does fork return? It returns 0. So in every child process, this print statement will execute. OS will be printed in every child process, right? Once, because that child process is a child only once. Next time it becomes a parent. Okay, so whenever a child is created, so OS will be printed. Okay, and when will NPTEL will be printed? NPTEL will be printed actually for every process in your system, right? All of the processes, when they would have finished the for loop, they would come here in the end, and every process will print NPTEL. So if your system has 4 processes, then 1 was the original parent and rest of them are the child processes. Okay, so the original parent would never print OS, it will only print NPTEL, while all the rest are child processes. They would have printed OS once, and in the end they would all print NPTEL. So for this particular example, OS will be printed 3 times, NPTEL will be printed 4 times. Does that make sense? So if okay, I'll explain again once. So I'm saying this fork equal to 0. This will be true for a child. It will not be true for a parent. It will be true, and if in the end here, in the end you have 4 processes. Okay, one of these processes, the P process, was your original process. Rest 3 processes are the child processes, right, which were created. Now when these processes were created for the first time, they were child. Next time when they create another process, they are a parent. Like C1 was a child here. C1 is a child of P, but then C1 becomes a parent of C2. So all of these child processes will print OS once. Okay, and all the processes in your system, they will finish the for loop, they will come here and they will print NPTEL. So that means if your system has n processes, or say m processes, then NPTEL will be printed m times and OS will be printed m minus 1 times. Okay, so I'll just write here. So we can conclude that NPTEL is printed m times if m is number of processes, and OS is printed m minus 1 times, where m minus 1 is the child processes that were created. I mean, these are all the new processes which were created by fork. Okay, new processes or child processes, you can use anything which is less confusing for you. So is there a comment? Got it. Okay, great. So then your question, since it has n value here, okay, it's not it wasn't 3, so now you have to answer it for n. Okay, now try to answer this for n. I'll copy here the I'll just copy here your, I mean, you know the answer already, but anyways, it's right there on the screen, but still I'll just copy it here, and then which one of the options is correct and why is it correct. for the original question. What is M? If it is not clear, you can tell me, I'll explain again. Anyone? What will be M? What will be the total number of processes created when for the value n here? The loop iterator is n. The loop maximum is n. Anyone? Yeah, n is the number of processes. No, sorry. N is not the number of processes here. N is some value given to your program. Okay, it can be some value, 1, 2, 3, 4, 5, whatever. But that is the number of times this for loop is executed. And as we discussed here, it depends on the number of time the for loop is executed. Like the number of processes created depends on the number of time the for loop is created. Here, if n were 3, then this would have been the process tree, and then 4 processes would have been created in your system. Now I am saying if n is some arbitrary value, then how many processes will be created? And then I explained that NPTEL is printed m times if there are m processes, and OS is printed m minus 1 times, because each new process prints OS once. Okay, I'll just go over here. So you must have in your algorithms or data structure courses, when you studied about tree data structure, then you must have learned how many nodes a tree have, how many leaf nodes a tree have, depending on the height of the tree and all of those things, right? So here in this case, I'll just draw a very simple I'll just draw an example here, a binary tree, complete binary tree. Okay, so you will have a complete binary tree here, right? All the levels are full, including the last level. Every level is full here. So here on the first level, which is level 0, then level 1, level 2, level 3. How many nodes are there on level 0? There is only one node, which is 2 to power 0. On the second level you have two nodes, 2 to power 1. On the level 0 you have one node, 2 to power 0. Level 1 you have two nodes, 2 to power 1. On the level 2 you have 4 nodes, which is 2 to power 2. And on level 3 you have 8 nodes, which is 2 to power 3. Whiteboard is not updating. Yeah, so it got updated. Anyways, yeah, so here you will have 2 to power 3 nodes on level 3. In your question, there are n minus 1 levels, because this I is equal to 1 is level 1, then 2, then 3, and you will have n minus 1 levels, because I is equal to n minus 1 iteration will run. When I become n, your loop will break. Okay, so you will have here level n minus 1, and then you will have a lot of leaf nodes here. All of these leaf nodes are what? These are all the processes in your system. These are all the processes which would have been created, including the first process, and this will be 2 to power n minus 1. Your system will have 2 to power n minus 1 processes. So then if 2 to power n minus 1 processes are there, then NPTEL is printed 2 to power n minus 1 times, and OS is printed 2 to power n minus 1 minus 1 times, which means this third option, it should be the correct option. This is the number of times OS is printed, this is the number of times NPTEL is printed. Is this clear? Any doubts in this question, explanation? Any doubts, anyone? Okay, thanks. Then I hope it is clear. If it is not, you can just let me know. I'm happy to explain again. But if there are no doubts, then let's just move on to the next question. This is a easy one, and so here it's a match the following, and if you have gone through the lectures on process states, then you would be able to easily answer this one. So I want all of you to try and answer it in the chat box. You can write option number 1, 2, 3, 4, or A, B, C, D, E. Don't need to write the whole option. Okay, just write which of the 4 options is correct. You can write A, B, C, D, or 1, 2, 3, 4, like that. These are, on the left hand side you have the process states, on the right hand side you have the explanation for that process state. You have to match the following. Any answers? Have you gone through the lectures for the week 3? Anyone? Like, what is new? Ready, running, sleeping? Or is everyone sleeping? Try to answer. Option D. Okay. More people, can you try? Don't be afraid of getting a wrong answer. Okay, yeah, option D is correct. So new So new means a new process is created. Okay, so it is C. Ready. What does ready state means? Ready state means that the process has been created, it is ready to execute, but it has not yet been given the processor. So it is there in your queue, in the ready queue. So you have a ready queue, that is, the ready queue has all the processes which are ready to execute. Okay, and then you have a scheduler in the OS, inside the OS. So it is the job of the OS to schedule these processes on the processor, right? So the scheduler will then decide which one of the ready processes to run next. Okay, so ready means that the process is ready to be executed, so it is waiting. Okay, so D option, it is waiting to be picked by the scheduler. So it is ready, but it is waiting for the scheduler to pick it and then assign some processor where it can run. Now the third one is running. So when your process is ready and the scheduler picks that process and then it assigns a processor, then the process will start running on that processor. And that is the running state, when it is actually executing. So that is running, that means it is currently executing. So option number B. And sleeping. So the sleeping state means that your process is sleeping, means it is not ready for execution, it is neither executing. Okay, it is in a sleeping state, means it is not ready. The process is created, it's not a new, it's like it is already created, it is part of your system, it is there in your system, but it is not ready, it is neither executing. There is another state called sleeping, where it is waiting for something, like it can be waiting for an IO. So it is possible that your process needed some data from internet or maybe from disk or any other device. It needed some input, or so it is waiting for some IO. So while the process is waiting for an IO, the process will not be doing any work, right? It will not be executing any instruction, it would be basically waiting for the IO. So to manage the OS, to manage the hardware resources better, that is the processor utilization, CPU utilization better, what OS does is that whenever a process is waiting for IO, it removes that process from the processor, moves it to another state, which is the sleeping state, and then it can assign another process to that processor. So another process from the ready queue can be moved to the CPU, and that process can run. Whenever the IO has finished, whenever the IO operation finishes, then the sleeping process will be moved to the ready queue. Now in the ready queue, when it is available, then it will wait for its chance to be given a processor. So that is the simple, I mean, there are more states actually in your process state diagram. If you would have different states in the processes, different process state, and if you would learn about the process life cycle and everything, there are more states there. But this is what these different states mean. So option number 4 is correct, 4A. Is there any question about this? Any doubts in this question or the explanation? Option number 1. So Deepika, is it clear now that why option number 1 is not correct? I think 1 was new is waiting for an IO. So new means the process is being created. 3B and 4 is okay. I think these two were new is actually process is being creating, and sleeping means waiting for an IO. Okay, let's go to the next question now. And here, state true or false for a process currently in running state. So if your process is currently in running state, that means it is actually executing on the CPU. At that time, if a software interrupt happens, so what does a interrupt means? So interrupt means some signal. I mean, the process was interrupted. It can be interrupted by what? Maybe some other code need to be executed, some other uh, one second, different software. I'm not able to, like, software interrupt examples maybe. Yeah, so an interrupt, like software interrupt, there's a hardware interrupts. Yeah, so software interrupt, like, yeah, if your process is running and it has asked to open a file or something, for that, that means the processor, the OS support is needed, right? For to serve that, to open a file or something which is there in disk, the device drivers, etc., or the other part of the kernel might be needed to execute. So at that time, the question is saying if a software interrupt happens, then it will result in the change to ring 1. So that is true or false? Is it true or false? If your program is running and a software interrupt happens, then that will result in change to ring 1 or not? Okay, so just so in your system, in your architecture, there are different privilege levels. There are different layers of privileges. Okay, that is your processor. It can run in different privilege levels. Okay, and in specific to x86, that is the Intel architecture, the privilege levels which are available, or the privilege rings which are available are ring 0 to ring 3. So ring 0 is the most privileged layer, then ring 1, ring 2 and ring 3. So ring 3 is the least privileged, and your user applications run in the least privileged, that is the ring 3, and your software like your privileged software, which is the OS, that runs in ring 0. Okay, so when a interrupt happens, then the interrupt handler will have to be invoked. Okay, I mean, even if a system call, so a software interrupt, it can be a system call. So when that interrupt happens, that time the system call handler will be called, right? And the system call handler or the interrupt handler and the code to handle these interrupts and system call, that is part of the kernel, and the kernel is actually the kernel runs in ring 0. Okay, so that will result in change to ring 0, not ring 1 here. So therefore the answer is here false. Now next question is, in the absence of system calls, a user process can never dynamically allocate memory. Is it true or false? True, false, is it? Okay, now I think you answered for the last question. Now try to answer this for the fifth question. In the absence of system calls, a user process can never dynamically allocate memory. What is dynamically allocated memory? true. Okay, answer is true. Others? Okay, yeah, that is right. So, in the absence of system calls, a user process can never dynamically allocate memory. That is true, because to allocate memory, new memory, uh, the user process needs to call the OS, because the OS is the manager. The OS manages the memory. So whenever a process needs more memory, it needs to ask the OS to give it memory, right? So, and what does OS do? So you know about paging. So whenever the process is asking for some new memory, then the OS will allocate that memory, and that is the pages, and then it will map those pages in the process address space, and it will fill the page tables, etc. So the since the whole control over memory is with OS, and only the OS can allocate memory. So if the OS does not provide that service to the application that it can request memory, that is, if it does not provide any system calls to the process to request memory, then the user process will not be able to dynamically allocate memory, dynamically ask for memory. That is at runtime. It won't be able to ask for any memory. So, therefore, the answer is true here. If it's not clear, then let me know. And okay, moving on to the next question. The wait system call inside the parent process returns the PID of an exiting child process. Okay. Which of the following best fits when wait is called inside the child process? So what is the wait system call? And the question is about the wait system call. It is saying that when the wait system call happens in the parent process, it returns the PID of exiting child process. And if the wait is called inside a child process, then it has given you certain options that which of the following will can happen. Option third. Okay. Okay. So, any more answers? Okay, so the what is a wait system call? So the wait system call actually, I'll have to sign in what? It's too much. Okay, yeah. So call to wait blocks the calling. So what is wait system call? So whenever your process, when your parent process, when a process creates a child process, and then it wants to wait for that child process to finish execution, that is to terminate, then it can call the wait system call. So wait system call means that it will be waiting for the child process to finish. Okay, the parent will be waiting for the child process to finish, And when the child process, so since one process can have multiple children, so whenever one child process will exit, the wait will return to it the PID of the child that exits. Okay, so a call to wait blocks the calling process until one of its child processes exits or a signal is received. After child process terminates, parent continues its execution after wait system call instruction. So whenever a child process will terminate, it will get a signal back saying that this process exit and this is the PID. So the return value will be the PID, and after that the parent can continues its execution. Now the child process may terminate due to number of reasons. It just exits or something else. Let's not worry about that. But what happens here is that first the fork system call will happen. The fork system call will create a child process. Then in that child process, we have like the exec will happen. That means the after the fork we do exec. So exec means the process will start executing. After that, when the process will exit sometime, maybe the process just terminated, and meanwhile the parent will call wait, so that it will be waiting for the child to exit. Okay, after that, when the wait system call is there, the parent will be waiting, like next instructions will not execute, it's just waiting, and once the child is exits, then it will resume the execution. Now the question here is asking that the wait system call inside the parent process returns the PID of an exiting child process, which is true. Okay, now if the child calls a wait system call, then what happens? That's the question. So there are options. So let's start from the last option. It says such a call is not feasible and is likely to crash the process. So this is not true. Like if you call a system call like wait or these, so if the process is not allowed to make that call, then the return value will be -1, saying that you are not allowed to do or something. So it's the call itself will not crash the process. Okay, then the option is return the exit status of the parent currently exited. So the wait is not waiting for the parent to exit or not. The wait system call is waiting for the child process to exit. It's waiting for a child. Okay, so therefore the third option is also not correct. Then it's return its own process ID. So wait system call is not it's not like it's not a the functionality of return wait is not to return the PID of a process. So that is also not correct. So first option is returns -1 when the child is not parent of any other process. So if the child was a parent of any other process, then it would have returned the PID of the exiting child. But if it is not a parent of any other process, then wait will simply return -1. Okay. So option 1 is correct here. None of the others are correct. Another option which could have been correct was that if the child process has a child, like if it has a child, then its PID will be returned when it exits. But here the option says when the child is not the parent of any other process, then it returns -1. So this is also true. So option 1 is true. Any questions about that? Okay, moving on to question number 7. A student has written a program and used PID equal to fork function call in it. The PID returned by fork was 5129. Which of the following is true about the process invoking fork? So it's saying that you have written a program and you have this statement here, PID equal to fork. Now when you print the value of PID, it is 500, it's something like 5129 or something. So it is saying which of the following is true about the process invoking fork. Your options are, first is process is a parent process with PID 5129. Process is a child process, its parent's PID is 5129. Process is a parent process, its child PID is 5129. And process is a child process with PID equal to 5129. Any answers? So here you have like similar, like you have PID equal to fork. You have some statement here. So the original program which is calling fork, that is the parent, and the new, so the original process which is calling fork is the parent process, and the new process which is created is the child process, right? So the original, it is, the question is about the process which invoked fork. So the process which invoked fork is a parent process first of all, right? So the option number 2 and 4 cannot be correct because they are saying that process is a child process. No, the process is a parent process if it has invoked fork. Now 5129, the PID returned by fork is 5129, okay, and that is the PID of the child process. So process is a parent process and its child PID is 5129. So option 3 is correct here. That we had discussed here, right? The fork returns 0 to the child and the PID of the child to the parent. So option number 3 is correct. Now next one is, when the child process state is set to zombie, all page directories and kernel are also deallocated. Is it true or false? What is a zombie process? How is it created and what happens? Any answers? Okay, let us look at, yeah, zombie process. Okay, so a zombie process is a process whose execution is completed but it still has an entry in the process state. Let's look at this diagram. Okay, let's look at this diagram. So we have a parent process. The parent process has invoked fork. So when fork is invoked, it creates a child process. Then the child process exec system call is executed so that the child process start executing. Okay, then the child process is executing. After that, when the child exits, that is, it terminates, it finished, that time the child process becomes a zombie process. So it's like that the process is still there but it's not executing. So, and if the parent is waiting, then the parent will, if the parent is waiting, then it will be informed, and at that time when the parent is informed, the parent will then remove all the resources which were allocated to the process, they will be removed, like page directory and page directory and all the mappings, etc. But if the parent is not waiting, and then the parent terminates, and the child is there, and the child then terminates, then but the child resources will not be allocated. So it's like the parent terminated, the child is still there, the child executed, but now no one is responsible for cleaning up the child resources. So at that time, that is called a zombie process. Like it's present there, but it is not executing, and it is taking up resources in your system, like process id and process page directories, etc. There's a memory, etc., but it's not executing. So that's a zombie process. A zombie process is a process whose execution is completed, but it still has an entry in the process table. Okay, zombie processes usually occur for the child processes. Zombie processes usually occur for child processes, as the parent process still needs to read its child exit status. Once this is done, using the wait system call, the zombie process is eliminated from the process table. This is known as reaping the zombie process. Now, there are some things that we can learn about zombie process. All the memory and the resources allocated to a process are deallocated when the process terminates using the exit system call. But the process's entry in the process table is still available, and this process is now a zombie process. So when the process is finishes the execution, the child process finishes the execution, it exits, and that time all the memory and the resources that were allocated to that process, they are actually deallocated, but the process entry in the process table is still available, and the process is now called a zombie process. Okay, the exit status of the zombie process can be read by parent process using the wait system call. And if the parent is waiting for its child to finish, then the exit status will be sent to the parent. After that, the zombie process is removed from the system, and then the process id and the process table entry of the zombie process can be reused. Okay, until then the process id and the process page directory, etc., they cannot be used. If the parent process does not use the wait system call, the zombie process is left in the process table. This creates a resource leak. If the parent process is not running anymore, that is, it finishes, then the presence of a zombie process indicates an operating system bug. This may not be a serious problem if there are few zombie processes, but under heavier loads, this can create issues for the system, such as running out of process table entries. The zombie processes can be removed from the system by sending sig child chdld signal to the parent. Using the kill command, if the zombie process is still not eliminated from the process table by the parent process, then the parent process is terminated if that is acceptable. So all of this, so if anything is not clear, you can tell me. But it means that when the child process is running, and if it exits, and if the parent is not waiting for the child, then the child resources like memory, they are deallocated, but the process entry is not deallocated. In your system, that process will still be shown, like this process is there, the process entry is still there, and now since that process is not executing, it's terminated, but entry is still there, so that process is called a zombie process. Now the question here is asking, when the child process state is set to zombie, okay, that means it has exited, it is now a zombie, all page directories and the kernel are also deallocated. Whether is it true or false? So this is true. Any other answers? Okay. Okay. Yeah, so the answer here is false because, as we just discussed, that first the kernel will not be delocated, right? Only the process memory which belongs to the process that will be deallocated, and also the the process is still there. So the process um, ID is not deallocated, and the page directory, since the process is still there and some of the mappings of the process are still valid, like the memory which I'm a bit one second. So here the kernel is not deallocated and the zombie process only has memory, uh, only the process ID of that process is not deallocated, that it still has an entry in the process table, like all the processes which are there in the system, it still has an entry there. All the other resources of that process, uh, including the process directories, page tables, etc., those will be removed, but only the process ID is there and the kernel is not deallocated, right? It cannot be relocated. So this statement overall is false because it's saying that the kernel are also deallocated, which is not true. The kernel is not deallocated uh, because the process is a zombie. Okay, so yeah, so let's look at this question. How many are left? Which of the below statements is false? So you have to tell a false statement, not the true statement. First one is kernel stack can be used to store the context of a process. So what is the context of a process? A context of a process means the register value of that process. Okay, so it is saying the kernel stack can be used to store the context of a process. Then the second statement is user stack is used to store the function details during function calls. Third is kernel stack is used to store the function arguments during system calls. And the last one is context of the process is useful to restart the process after some time. So which one is false? So first statement, kernel stack can be used to store the context of a process. Is it true, false? Third statement. Yeah, so third statement here is false. And the first statement is true because the kernel stack, that is the kernel memory, that can be used to store the context of a process. So when is the context of a process stored? Context is stored whenever the processes need to be switched. When the OS stops one process, running process, and in place it switches it to some other process, like some other process is executed. So that is context switch. When one process is stopped and another is started, that is a context switch from process 1 to process 2. Now when the processes are switched, when a context switch happens like this, then the state of first process needs to be stored. That is, the value of the registers in first process needs to be stored, and the values of the another process need to be restored. So the context here means the register values of that process, they need to be stored. Now they will be stored somewhere in the kernel memory, or maybe in the process memory also. Or no, then they actually stored somewhere in the kernel memory belonging to that process, or it can be stored in the kernel stack also. So it's saying that it can be stored. Yes, it can be stored because the kernel is storing the context and it can store it in the on the kernel stack. So first statement is true. Second one is user stack is used to store the function details during function calls. So which is true. Whenever a process is executing, and if it when you call main, when main function is executing, if the main function calls some other function, say foo, then you will have one frame, one stack frame, right? You will have for main function. When main calls foo, then you will have another stack frame for foo function, and all the details of these functions, they are stored in the stack. So the user stack has all the details of which functions are being called, and all the local variables and return addresses are stored on this user stack. So user stack is used to store the function details during the function calls. That is true. The last one is the context of the process is useful to restart the process after some times. So sometime, yes, that is the reason why the context is saved. So when one process is running, so that process has some state, right? Some values of the registers, etc. Those need to be saved, and when that process is started again, those need to be restored. Otherwise, if you do not save and restore, then the register values of process 1, if say register 1 had value 100 and you do not save it, then another process will start executing, and that process might change the register value to some other value, say 200, 300 or something, and then your first process, when it starts, it will see the register value has changed and its execution will not be correct. So when processes are switched, that time the context of the process need to be saved and it needs to be restored after some time when the process is restarted. The third option is kernel stack is used to store the function arguments during system calls. So when system call happens, at that time the user application is calling it's calling a system call. So the argument to the system call, they cannot be saved in the kernel stack. Why? Because your user application doesn't have access to the kernel memory, right? User application, it cannot access the kernel memory. So arguments for the system call, they are saved either on the stack of the user application or they are present in the registers, and those it is passed, the values, the arguments are passed to the kernel through the registers. So but it cannot be saved on the kernel stack because the kernel stack belongs to the kernel. It is the privileged memory, and your process, it is an unprivileged process. It's running in the user space. It cannot write to the kernel stack. So that's why the option number 4 is false. Sorry, third is false here. Is there any question? Okay, this is the last question for today. What is the output in the parent process? So this is the fourth question which we saw earlier, but it is a very simple one. And here you have the C program. Okay, initially you have int variable a equal to 0. PID is the process, some variable, okay, PID, and then you have a fork system call which returns some value which you are going to store in PID variable. Then you are checking PID variable equal to 0 or not. If it is 0, then you are going to execute these two statements. Otherwise you are executing these two statements. Okay, in the first, when if is true, at that time from a you subtract 10 and then you print the value of a. Otherwise you add 10 to the value of a and print a. And these are your options, that what will be printed. Here u equal to %d, here x is equal to %d. So you have u and x is also different. In your options here, your u and x should have been small u and small x. They are capital U and capital X here, which is actually a typing mistake. But this is the question, and here the output of the parent process is asked. Okay, so what will be the output of the parent process? Third option. Is it for this question or last? I think that was for last question. Okay. U equal to 10. Yeah, that is correct. So here, since the question is for parent process, so when fork is executed, fork will return here what? If it is a parent, it will return the PID of the child. If it is the child process, fork returns 0. So in the parent, fork will return the PID of the child, which is a non-zero value, positive non-zero value, right? And therefore PID, when you will check here, if condition will become false. If condition is false, you will come to the else block. Here a will be incremented by 10, and when you print, you will print x is equal to 10. U equal to 10, no, x is equal to 10 should be there, no. Here you have u, here you have x. Is that clear? I mean, the a will be 10, 10 will be printed, that's right. But here x is equal to 10 should be printed. Is that clear? Okay. Okay, so if there are no doubts, how to build logic like human. Okay, so if you're talking about the explanations, then I think that will come. I mean, so when you will study the material, and once you start understanding the material, I mean the when you're taking the lectures, and you if you understand them, and then you try these questions, and not just these questions, I mean, try to read more, try to understand the how OS is all of these topics in OS, processes, memory management, virtual memory, etc. As you will learn more, I mean, if this is the first time you're taking the course, it can be very difficult, but once you will finish the course, then you read, when you're taking the course, if you accompany it with more study materials, maybe some other book or anything like that, then slowly I think you will start understanding the concepts better. And then when you understand the concepts better, then you will be able to answer questions like this, or you basically have a better depth, better knowledge of the topics and the concepts, and then you will yourself be able to explain everything here that we discussed today. But I mean, this is not something which is I mean, that is, I'm saying, is very natural once you understand the topics, and once you read about these topics and understand. Have you done BTech or BCA? So I'm currently a PhD student in IISc Bangalore. I have done BTech, MTech, and now I'm doing PhD. And I work in computer system security. So yeah, that's my background. My background is in CS only, from BTech in CS, MTech, and then PhD in CS. So if there are more, so I can take more courses. Sorry, I can take more questions, but I'll just stop the recording. Uh, okay. Think here.